Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are 5 modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hello and welcome to class 7 of my physics 1 courses. And still in the last 6 classes, so we have been concentrating on the most modern topic of physics called quantum physics. We are in the first year. I have been telling you that I am offering you the quantum mechanics 1 courses, which is essentially some theories you are talking about. The theoretical development of quantum physics from 1900 to 1927, that is included in your course. Till now, I talked about 2 experiments. One of them is photoelectric effect. One of them is Planck's explanation of black body radiation. That is a first-hand knowledge of where from the quantum concept came in. Planck told that energy of an object can be discrete. E is equal to NH in abbreviated form. We told you, which is a complete departure from classical physics concept. Classical physics told the energy of the, it may be from thermodynamics, energy may be 3 by 2 kT at any temperature, and T can be anything, energy can be anything. Energy may be from harmonic oscillator energy, half ohm omega square. Anybody can oscillate with any energy frequency, so it should have any value of energy. So this any word was removed by Planck. Okay, he told that energy could be discrete. So later on, I discussed another experiment, particularly last video lecture. If you follow, we discussed about a very popular experiments of your very popular experiments. That is the photoelectric effect experiment, okay, which you know. But the main message of that experiment is that in that experiment we discussed that light is not a wave; it's showing the photonic nature. What photons are doing? They're colliding with the electron. Who collides? Matter collides. So it's an exhibition of the material nature of the. It proves that over some time a wave can be metal-like. So today, our objective of the class is to explore another experiment called Compton effect, which will further establish this photon concept or material nature of the known wave or material property of the known wave. Now, this is our 7th class in a row. This is me, and for as I mentioned every day, you can always contact me in my mail ID is written here or in my mobile number. There is also my WhatsApp number. Okay, you can always contact me. So first we salute Planck, okay, because he is the father of quantum ideas. Okay. So now, if you now just see, this is the experiment of black body radiation that was done, and this is all the radiations are coming out. It plotted, and ultimately we wanted to calculate the total energy in the Planck's experiment, total energy in the black body radiation experiment. And our problem was that we did not have a right expression of V lambda. We tried to get it, and Planck was the person to give it the correct formula with that idea that energy could be discrete. This idea is the first breakthrough in the development of physics. Okay, that energy can be discrete. Okay, energy of an object could be discrete. Okay. Now, if I further progress, okay, that is then they have this is energy is discrete. Okay. Now, then we divided physics into 2 parts: before 1900 and after 1900. Before 1900 is classical, and after 1900 is modern. What is your classical physics concept? Two things are there in the of nature: matter and waves. Matters are defined by their mass, momentum, size, shape, and waves are defined by their wavelength, frequency, and phase. Okay, example of waves are light wave, sound wave, that is electromagnetic wave and acoustic wave. Matters do collide, so its best exhibition of the material nature is the collision, and the best exhibition of the wave nature is the superposition. Okay, just to remind you, matters can collide, okay, waves can superpose, okay, and wave on a matter makes scattering. Okay, these things I told you. Okay, this is a scattering phenomenon. Okay, so now these ideas of classical physics all got a huge departure the moment you cross 1900. So what we did, okay, this is the classical concept on the top. Now there will be departure from this to experiment. Photoelectricity I already discussed, just to remind you, okay, that what photoelectricity tells you, it's a wave incident on a matter. So you thought it's a scattering going on, but unlike to normal scattering, you get an electron emission. And today you know how did Einstein explain it. Initially we thought it's a scattering process, but in a scattering process we should get reflected beam, rather you get electron emission. So there must be something else happening. That else was explained by Einstein. That incident radiation that is coming in, it is basically it's a stream of photons coming in. Okay, photons are basically each photon is having h new amount of energy. So what photons are doing, they're hitting the electron. So it is a photon electron collision process. Who collides? Matter collides. You are thinking a photon as a matter. So matter photon is hitting the electron, and if the electron with that energy will absorb the because of the collision, electron will take up energy from the photon. It will overcome Coulombic attraction of the nucleus and get out, okay, of the metallic system. So this is the famous Einstein's photoelectric equation that you get. So the important concept of the photoelectricity is the photon concept, that energy, light means stream of discrete packets of it's a discrete quanta of energy, okay, and photons are like making electrons colliding with the electrons. So who collides? Matter collides. Okay, it's an exhibition therefore of the material nature. Okay, because only matters can collide. Okay, and these ideas are now further being established through the Compton effect experiment. So this is something. So photoelectricity is showing this departure. Okay, wave can be metal-like. So that is a takeaway from photoelectric effect. Now it will be further established that wave could be metal-like. We need further justification of it. That is what we are doing through Compton effect experiment. Now this is experimental setup of Compton effect. Just to study Compton effect, you see same thing is happening. Okay, you see the setup. Okay, you see two things are there. Left hand side, photoelectric effect. Light, photoelectricity was done with ordinary light. Okay, you see a pink colored light have there shown there. That means a visible light is falling on a metal. Electrons are coming out. And they are passing to the circuit. You get a current. That is photoelectric effect. But X-ray is a very similar optical phenomena. There also photons will be coming in. Radiation will be coming in. But in Compton effect, it is the X-rays that comes in. So there, left-hand side picture is a photoelectric effect where the optical wave, that is ordinary light, hits the metal. In the right picture, what you see, here X-ray hits a atomic system. Now, unlike to Compton photoelectric effect in Compton effect, so therefore you are preferring X-ray, not ordinary light. Why X-ray? Why not ordinary light? That is a question to be answered. And here in photoelectricity, the radiation was incident on a metal, but Compton effect study was done with carbon atom. Okay, why carbon atom, that will come to know. But ideally, if you see side by side, both the phenomena are very similar. Okay, wave on a matter. Okay, now now obviously one more concept comes in. What is an X-ray? Okay, okay, X-ray is an electromagnetic wave. Okay. Okay, X-ray is an electromagnetic wave. I told you earlier also, electromagnetic wave is a, you see, our ordinary light is also an electromagnetic wave. Only point is that wavelength of ordinary light is between 4,000 to 8,000 angstrom. Below 4, that is the wavelength. Below 4,000 you have got the X-ray, gamma ray, etc. And above 8,000 you got the infrared light, radio frequency or heat wave, etc. Now X-ray is therefore, so basically ordinary light and X-ray are members of the same family. Only thing is that X-ray has got more energy because it has got wavelength is lesser because of that formula E is equal to h nu or E is equal to hc by lambda. So that means X-ray is more, okay, it has more rich, it has got more energy, and ordinary light is less rich, less energy. If you follow the basic formula of photoelectric effect, E is equal to hc by lambda, or basic energy of the photon concept. Okay, so basically The idea is that the X-ray is an electromagnetic wave, and but its wavelength is very very small compared to the wavelength of ordinary light. Wavelength is of X-ray will be between zero point 0.1 to uh, 1 angstrom, okay, like that. Okay, see, zero point 0.1 nanometer means like 1 angstrom. So it is zero point 0.1 to 1 angstrom, that is the wavelength of X-ray. So on the contrary, wavelength of visible light is from 4,000 to 8,000 angstrom. So wavelength of X-ray is 1,000 times smaller than that of the wavelength of the ordinary light. So this term wavelength is, you can see the picture. This is the wavelength. The wavelength is becoming shorter and shorter and shorter. So for X-ray, you see, I am not doing a basic departure. I am also working with electromagnetic wave, but it's a wave, electromagnetic wave having more energy, okay, because its wavelength is less. Now it is incident. What happens in Compton effect study? You see that blue one is X-ray coming in. Okay, if you look at the picture, X-ray coming in. Okay, this is the X-ray coming in. This is the X-ray coming in. So basically, these X-ray. Okay, this is the X-ray coming in. It is incident on one of the electron of the carbon atom. Now this electron is contributed by carbon atom. Okay, so to you this phenomena is like that right hand side picture. A wave is incident on a matter. You see, look at the picture, similar to wave on incident on a matter. So we expect a scattering phenomena because wave on a matter. Okay, so we anticipate a scattering phenomena is going to take place. Okay, so wave on a matter, so we anticipate a scattering phenomena is going to take place. Okay, I hope you understand. And to make you happy, it will be scattered also. If you look at the Compton effect experiment, it will be scattered also. The wave incident on a matter, and it is getting scattered just like this from the sun. That is the source of light. Some red light is coming in. Suppose the wavelength of red light is say lambda. Okay, it is coming in and it is getting scattered. Okay, if you draw a normal here, okay, so ultimately it is getting scattered, and the wavelength of this is the scattered beam. Okay, so this is the incident beam, this is the scattered beam. So here also X-rays are coming in and being scattered. Okay, so therefore what you notice here, you see that X-ray is coming in. These are the X-rays coming in. If you look at the picture, X-ray coming in. Okay, and now it is incident. This is the electron, one of the electron here. Electron provided by the carbon atom. So it seems to be a scattering phenomena. Okay, just like the here some radiation coming in. Okay, and being scattered from, because it's a surface. Suppose it's a mirror, for example. So a wave is incident on a matter, and I get a scattered beam. So it's a red light coming in. The reflected color is also red. So now, so therefore, we anticipate that, okay, whatever you're thinking that a wave is coming in and a scatter, I should get a scattered beam, that is happening. Okay, but is everything okay? Scattering is taking place in both the picture. You notice in the left hand side it is, right hand side it is, the ordinary light is getting reflected, so it's a scattering phenomena. In the left side it is the X-ray being getting scattered. Question is that, are these two pictures okay? Because in both the cases scattering is there. Okay, if you don't understand, let me just show you. Okay, that what is actually happening. Okay, just a second. Now what is happening is this much, that Suppose I've got a radiation incident of wavelength lambda, and suppose this is the matter. Radiation is incident on a wavelength lambda, and suppose this is the matter. Suppose this is incident on one of the electrons. Now, if it is incident on a matter, so what will happen? This is the direction of incidence. Now, what normal scattering theory tells me that after incidence, it is not going to maintain the same path. Rather, it will be deviated. And this alpha is the angle of scattering. So this is my incident ray, and this is the scattered ray. So if I draw a line here, to the left of the line, it is a situation before scattering, and this is the scattered ray. So this is a basic definition of scattering. Now what I am doing, now I am talking about the Compton scattering or Compton effect. Now in Compton effect, a very similar phenomena is there. But in Compton effect, so what is happening? Suppose this is your X-ray coming in. In the I told you X-ray is wavelength is very, very small. So this is the incident X-ray. Now the X-ray is monochromatic in nature. What does it mean by monochromatic X-ray? Monochromatic means is lambda is fixed. So X-ray of definite wavelength lambda is coming in. Okay, X-ray of definite wavelength lambda is coming in. Now this is incident on one of the electrons. Now suppose it is incident. Suppose this is X-rays coming in, and this is one of the electrons. Now this electron is provided by carbon atom. And unlike to photoelectric effect where electrons are contributed by metallic atom. So now this electron, what would happen? We consider this electron is at rest with some mass, say m0. M0 is called the rest mass of the electron. So what would happen? This line is the direction of incidence. So what would happen? You see this picture is a wave is incident on a matter electron and getting scattered. Here also wave X-ray is incident on a matter electron. So it is expected to get scattered. It was scattered also. So it was scattered. So this is the scattered beam. Okay. So now the question is that if you look at the phenomena, now the question is that here a wave radiation of wavelength lambda coming in and it is getting scattered. Here also a radiation of wavelength lambda coming in and getting scattered. So if I draw a line here again, to the left of the line it is a before scattering phenomena, and to the right of the line it is after scattering phenomena. Here also to the left of the line before scattering phenomena, to the right of the line after scattering phenomena. Now I request you to check both the pictures. So this is the basic definition of scattering, and this phenomena is the Compton scattering. Now question is that, do you see any difference? Can you see any difference in my drawing? Here radiation is coming in and getting scattered. Here also radiation is coming in and getting scattered. You may be saying here I am using any radiation, here I am using X-ray, but that is not the difference. Any other difference? Yes, just think about it. Any other difference is there? Difference is there. Clear difference is there. Here you see I have used same color for the incident beam and the scattered beam. But here I am used different color for the incident beam and scattered beam. What color resembles? Color resembles wavelength. Obviously X-ray does not have a color. But if you compare the VIBGO, the violet to red, who is having higher wavelength? Obviously red is having much larger lambda compared to violet. So it shows there that because of the scattering, the wavelength of the incident radiation, if it is lambda prime, it will be greater than the wavelength of the scattered radiation should be greater than that of the wavelength of the incident radiation. So scattered radiation has got larger wavelength or smaller frequency. Lambda prime will be less than greater than lambda. Corresponding frequency will be lesser than the frequency nu. So here alpha is the angle of scattering, but the difference is that the peculiar things are happening. The wavelength of the scattered beam and wavelength of the incident beam are different. Okay, now this is absolutely a new observation. Okay, because in normal scattering, if you say blue light on the wall, or as I was showing red light on a surface, scattered beam is always red. It does not change color. It will never happen. Blue light on a wall will become a orange or red. So color or wavelength does not change with ordinary reflection, but it is happening here. So this is something uncanny. So again, you see, if we use classical theory that it's a wave incident on a matter and will make scattering, and because of scattering is taking place, okay, fine, it's the scattering is taking place, but how do you explain this change in lambda? You can't explain. So same problem was faced by Compton. Actually, what happened? Okay, Compton got two kinds of rays. You see, when you do an experiment, you cannot send only one X-ray. You have to send few parallel beams of X-ray. Now, suppose these three beams, all of having wavelength lambda. So the one which is facing the electron is getting scattered. The one which is not facing the electron is unscattered. So to the left of this line, you get an X-ray of all the same wavelength. To the right of the line, you get two kinds of X-ray. The red one is obviously the unmodified X-ray. Another is unmodified X-ray, which is peculiar. It does not happen in daily life. I send red light incident on a wall and I get various colors, various wavelengths. I do not, it doesn't happen. Okay, this is called unmodified line, the blue one. I have into my drawing. Obviously, X-ray does not have a color. This is the modified line. So this is the peculiarity that was observed by Compton. Main problem is there is not with the unchanged lambda that is expected, which is happening here also. Main problem with the changed lambda. Okay, why it is happening? Okay, so that Compton tried to explain why it is happening. Okay, so it's peculiar. So again, you see, if you use classical theory, then it's a scattering process. In a scattering process, as you can see in the top picture, there will be no change in wavelength. Now it is happening here. Wavelength is changing. So with scattering theory, why this wavelength change is taking place, you can't explain. Okay, so you have to go again beyond the box. Okay, so I hope I have illustrated the problem to you. Now get back to the presentation PowerPoint again. Okay, if you get back to the PowerPoint, so this is the phenomena. If you see, this is what I was talking about. Okay, you get two kinds of X-rays. Okay, this is something I was talking about. This is the normal scale reflection or scattering, no change in lambda, but here also I've used different color. Wavelength is changing. So that is the peculiarity of Compton effect. Okay, so you get, as you can see in the picture, you get two kinds of X-ray. The blue ones, that is lambda i's or unchanged lambda, and the lambda f is with modified wavelength. Okay, you see, I'm silent about electron. Let me remain silent about electron. I'll talk about later on. Okay, about the electron. So the beauty is that if you look at the phenomena, this is happening in Compton effect. Okay, you see, you're getting electron is the blue ball is electron, and the yellow one is the radiation coming in. You see, it is changing its color. Okay, whatever I have been telling you, it is happening. Photons coming in, it is radiation coming in. Yellow one is becoming orange. Okay, wavelength is rising because it is losing energy towards electron is also moving. Okay, so I was silent about electron. Okay, so we'll talk about electron in let us talk a bit about the electron also, but before that we'll look at these curves. This is what Compton actually observed in his original experiment. Okay, what Compton observed, Compton got an additional peak there in his experiment. Okay, so unmodified line is the peak which is passing. It is noted there. Okay, this is the, you can see there. This is the unmodified line. Okay, this is the unmodified line, and this is the modified line. Why it is happening? That is the question. That is something uncanny. So that is something we have to explain. That is something which classical physics cannot explain. Okay, so now let me present to the definition of Compton effect. So what is happening if X-rays are coming in an incident on a light element? Light elements means few words are important. I am doing the experiment with X-ray. Why X-ray will explain later on. Now it is incident on carbon atom. Carbon atom, it is hitting the electron of carbon atom. Why carbon? It's because it's an element of low atomic mass. Why low atomic mass? We will explain that. But what is happening because of that? It is getting scattered. Okay, what is happening because of it is that it is getting scattered. Okay, so scattered radiation are two types, one with modified one and another with unmodified X-ray. Now in optics you often hear about a term called coherence. Any two or three beam could be called coherence if the wavelengths are same and if the phase difference remains constant. So if you look at the phenomena, To the left of that orange line, which is before scattering, all the X-rays are having same lambda. So there is a chance they satisfy the first condition of being coherent. Okay. If their phase difference remains constant, they could be coherent. But after scattering, you see, they could never be coherent. Okay, because who is the culprit? The red one is the culprit. Okay, the modified one. Because if you compare even the three lambdas I have shown there to the left of the maximum, left of the orange line that is before scattering, all of them are all lambda I the wavelength. So they could be coherent. But after scattering, because of the red one, there is a change in lambda. So first condition of coherence is that wavelength should be same. That is violated. So even if you begin with coherent ray, because of Compton effect, you will lose coherence. So this type of incoherent scattering, X-ray scattering is called Compton effect. Okay, but course doubt is that why wavelength is changing, that you can't explain. Okay, so that you have to explain now. Okay, why wavelength is getting shifted. So what Compton did, he actually calculated this change in lambda. Lambda final f is the final wavelength, lambda I is the initial wavelength. What you have to show wavelength is rising. So that calculation was done by Compton. He made two assumptions. What is the assumption number one? Compton thought that obviously he is doing it in 1923. So by that time, the Einsteinian idea of photon concept was there. So Compton has utilized that idea that it is the photons which are coming in, not just the X-ray coming in. Okay, so X-ray photons are hitting the electron there. So for X-ray are coming in, X with energy, X-rays are coming with some energy, some momentum. I'll show you the calculation now. So X-ray photon is hitting the another matter called electron. So basically, this is the first assumption. Okay, now before getting into the second assumption, let me talk a bit more about photons. What photon is? Let me define a photon properly. So now to talk about the photon, let us look at this calculation. After that, I'll talk more. So basically, if you look at the picture, that these incident X-ray means basically according to Compton, some photons are coming in. Suppose these are the photons. Photons are coming in. Each photon is having h new amount of energy and they are moving along this direction. Now photons are basically having, each photon is having h new amount of energy. So now let me talk a bit more about the photons. So photons are coming in. Photonic energy is h nu according to the photoelectric effect. Now, which is not included in your course, a bit of relativity idea, but that formula you know, that E is equal to mc square formula. Okay. According to relativity, if somebody is at static condition, according to relativity, if somebody is at static condition, suppose I have got a, you see, suppose this pen. Okay, can you see this pen? What this pen is? This pen is static in front of me. Now I am in this room, so this room is static. This pen is also static. So I am the observer. I am sitting in this room. So this room is called a reference frame. In this reference frame, I am the observer. So I am moving. The pen is also moving. So if I now measure the mass of the pen, it will be its original mass or rest mass. So now if somebody moves by cycle in front of my room, suppose he's moving with the velocity v, so he will see the pen. Suppose he's looking through the window or through the door, he will see the pen, but he will see a moving pen. If the cycle moves in this direction, okay, towards this direction, he will see the pen is moving in opposite direction. Okay, so what he will see? He will see a moving pen. So if he measures the mass of the pen, he will measure the mass of a moving body. That is called the relativistic mass. Okay. Now static mass or original mass and relativistic mass are connected by an Einsteinian formula coming from special relativity. If the static mass is say m, okay, if there is m0, okay, and the relative speed between the two between the cycle and the room is u, it is 1 minus u square by c square. This will be the relativistic mass. Okay, it is a separate discussion to talk about the relativistic mass. We'll do that. Okay, let me just talk a bit about this relativistic mass. Okay, let me show you a bit of calculation. After that, we'll come back to this photonic energy calculation. Okay, so the basic concept of relativistic mass and static mass is needed. Okay, otherwise, when photon is associated, it is also moving. So many, you see, This formula is talking about variation of mass. Okay, which is very funny and interesting because of relative motion. So now let me just show you with some calculation. Okay, to be easier for you to understand. Just a second. Okay. Z direction, and in front of me, suppose I am looking at a ball here. Okay, it is on a table. It is kept static. So now, if I now measure the mass of the ball, so I am in the static. I am static. This ball is static. I am also static. So both observer and the object are in the static condition. Okay. So if I am measuring the mass of the ball, I am measuring the mass of a static ball. Okay. I will measure the mass of a static object. So if I measure the mass of the body, I will measure its original mass, which is called m0, the rest mass. On the contrary, suppose in front of me, suppose along this road, okay, along this direction with a velocity u, a cyclist is moving. And so if the cyclist moves in this direction, he will see the ball is moving in the opposite direction, okay, with a velocity minus u. So cyclist will see a moving ball. Now if you measure the mass of the ball, he will measure it as the moving mass. M will be the mass measured from a moving frame. Okay, this is the mass measured from cycle. Okay, from this moving frame of cycle. So this m is the mass of a moving object, and this mass is called, this m is called the relativistic mass, because this mass is coming because of the relative motion between the cycle and the object. Now this mass m0 and the mass m are actually connected by a formula like this: m equal to m0 by root over 1 minus u square by c square. So they are actually connected by this formula. So this is called relativistic mass variation. That is variation of mass due to motion. This is called relativistic mass variation. Now let us see how, when you can see the change in the mass. You can see the change in the mass in this case. Suppose again this is a reference, the classroom. This is myself, and on a table this is a ball, and this is a cyclist moving along this direction with a speed u. Okay. Or to make my life simple, suppose I consider this is myself, this is a table, and cyclist is moving along this direction with a speed u. So he is seeing the ball is moving with the speed minus u in this direction. Okay. So what is the mass measured by me? I am measuring the mass as m0. What the cyclist is measuring? He is measuring the mass as m. So they are connected by this formula, m0 by root over 1 minus u square by c square. Now it all depends whether mass will vary or not. It all depends on the relative speed u. U is the decider. Suppose a normal cycle, the speed is like 12 km per hour. If it is like 3 meter per second, if you calculate it in meter per second. So then your u by c will be like this much, 3 by 3 into 10 to the power 8. So it is of the order of 10 to the power minus 8. So if you calculate u square by c square, it will be of the order of 10 to the power minus 16. So now if you put it in this formula of m0 by root over 1 minus 10 to the power minus 16, it is almost m0. So for relative speed, for daily life speed, okay, that is a normal cycle moving, this m and m0 are same. I do not see any mass variation. Then the question is that when we are teaching it because you can see it in specific problems. Mass variation can be observed, okay, in specific cases. When you can observe the mass variation, it can be observed in specific cases like this. Okay, you can see the mass variation in very specific problem. Now that problem is this much. Suppose this problem. Okay, suppose again this is me, this is the ball, cycle is moving, I measured the mass as m0. Now this is the cycle moving, this is the cyclist is moving, this is a cycle. Okay, cyclist is moving in a cycle with a speed u. So he is seeing the ball moving with a speed minus u. Okay, so now what is happening? He is measuring the mass as m. Now the connection between the two masses, as I told you, is m0 by root over 1 minus u square by c square. Now suppose in the normal speed, when u was case 1 was like 12 kilometer per hour or 3 meter per second, then my calculation shows I have not observed any mass variation. Okay, so now then obviously second case is that when you can observe it if suppose I have got a super cycle. If the cycle moves with a speed close to the speed of light, say 10 to the power 7 meter per second, okay, it is a super cycle I am talking about. Say suppose it is moving at a speed 10 to the power 7 meter per second. Okay, suppose then your u by c will be of the order of 10 to the power minus 1. Okay, u square by c square will be of the order of 10 to the power minus 2. So your m will be now m0 by 1 minus 0.01, which is much more larger. So now, because you see your denominator is decreasing now, okay, it is becoming a fraction now. So m is appearing expected to be m0, mass will grow. So you can see the mass variation if somebody moves with very high speed, close to the speed of light. Okay, not exactly equal to the speed of light, close to the speed of light. Now our electron, orbiting electron, okay, electron when it's orbit around the nucleus, it is thought that orbital speed of the electron is close to the speed of light. Okay, it's like 10 to the power 7 meter per second. So for the moving electron, you can see this mass variation. Okay, so that's why in my quantum mechanics course, because I am talking about electron, this electron speed is close to 10 to the power 7 meter per second. For electronic journey, therefore, we anticipate this mass variation. Now, they also answer two questions, which is pertinent question is that if somebody, you see, you've been told in the school, if somebody moves with the speed of light, nobody can move with the speed equal to the speed of light or greater than the speed of light. Then what would happen to you? The answer is simple. It is coming from relativity. It will become 1 by 1. So mass will diverge, which is impossible. Okay, mass cannot be infinite. Okay, and if u is suppose u is greater than c, okay, then what would happen in this expression? M equal to m0 by 1 minus u square by c square. U square by c square is greater than 1 because u is greater than c. So u square by c square will be greater than 1. So what you are doing inside the square root, you are generating a negative. So basically it is becoming imaginary. Again, mass cannot be imaginary. That's why it is told that nobody can move with the speed of light or greater than the speed of the light. At least it can move with normal speed where you can see, do not see any mass variation, or if somebody like our electrons, orbiting electron, it can move with the speed close to the speed of light where you expect a mass variation. Okay, relative variation of mass due to motion can be seen in that case only. Okay, you can see this in case of electrons orbiting around the nucleus. So electron motion, okay, for that purpose you can see, okay, the relativistic mass variation. Okay, so now what Einstein did, he actually utilized this idea. What Einstein did, He utilized this idea. What Einstein did is this much. He utilized this basic concept of mass variation with velocity, m equal to m0 by root over 1 minus u square by c square. Okay, this is the relativistic mass or mass due to motion, and this is the rest mass. Now Einstein utilized this idea to get that famous equation of E is equal to mc square, where m stands for obviously the relativistic mass. And similarly, analogous idea is that if somebody at rest also, it will have some energy m0 c square. So this is the famous Einstein, you may call it E0. Okay, that this is a rest energy. This is the first famous Einstein's mass energy relationship, and this is the total energy. Okay, this is a famous Einsteinian idea of mass energy relationship. Okay, now if you utilize this idea, suppose I have got a photon moving whose mass is mp. So according to relativity, energy of the photon will be mp square because photon moves with the speed of light. Okay, and on the contrary, this is for a photon. We are considering mp is the photonic mass. Okay, so let it be the photonic mass. Now, from photoelectric effect, you know E is equal to h nu. So obviously both of them are photonic energy coming from two different theory of Einstein. This is coming from the relativity theory, and this is coming from photoelectricity. So both of them are same. So we can now write down, if we equate them, we can now write down. So therefore mp square is equal to h nu. Or from here on, we can also write down therefore mp into c is equal to h nu by c. Now mp, as I mentioned, is a photonic mass and c is a photonic speed. Mass into speed is nothing but the momentum. So this gives me the value of the photonic momentum. This is a photon momentum. So therefore, you see, I am defining everything for photon. Photonic momentum I give. And what is photonic mass? H nu by c square. Because c is high, h nu by c square will be very, very low, almost insignificant. But so what is photon? Photon is a matter with momentum, finite momentum, and very low mass. Okay. So what is happening in the photoelectric effect? You see, if you look back at the expression, what is happening in the Compton effect experiment? Okay, this is your Compton effect experiment. X-ray photons are coming in. Okay, these are the X-ray photons are coming in the Compton effect study. Okay, these are the X-ray photons are coming in. Now they are incident on one of the electron of the carbon atom. And what Compton is thinking, it is not photons coming in, rather, so not X-ray coming in, rather some photons are coming in. Each photon is having h nu amount of energy. Each photon is having h nu by c amount of momentum, and each photon is having some insignificant mass. So matter photon is incident on another matter electron whose mass is like 9.3 into 10 rest mass of electron, 10 to the power minus 31 kg. So ultimately it becomes a photon electron collision. So basically it becomes a collision process. And what Compton thought, its the nature of collision is elastic. Okay, so he thought that elastic collision is taking place. There is a second assumption, and because of elastic collision, what would happen? Okay, if the photons ultimately, this is the scattered photon. Okay, its energy is wavelength is reduced, so energy will be lesser than bit. Okay, so photon is therefore losing a bit of energy. Loss of energy by the photon is h nu minus h nu prime. So because total energy is conserved, this loss of energy of photon will be taken up by the electron, and now electron will also start to move. It was initially at rest. Now if I draw a line here, now it is a situation before the collision, and to the right of it, it is a situation after the collision. So after the collision, what is happening? Photons are moving with some angle alpha, electrons are also moving with some angle say beta. Okay, an electron should have some mass now. That is a relativistic mass, m0 by root over 1 minus a u square by c square, because u is the speed of the electron. So electron will also move now. So this is the story now. So with this in mind, let us get back to the picture. So therefore, you see the picture now. So photonic energy, relativity, energy of the is mp(c) square according to relativity, according to Einstein, and photoelectric effect h nu. So photonic momentum is h nu by c. Beautiful expression. Okay, mp into c, the photonic momentum. Again, photonic mass is h nu by c square. So photon is a matter, and this is what is happening in Compton effect. You see extra photons are coming in. It is hitting an electron. Okay, you see photons are coming in. Okay, it is coming with some momentum h nu by c. Photon is colliding with electron. Nature of collision is elastic. So photon is losing a bit of energy. So its color is manifested by the change in color. And electron is also dislodged, because loss of energy by the photon is taken up by the electron, and electron is moving. Okay. So the in my pitch in the animation, that yellow one is maybe the initial wavelength lambda I, the red one is the maybe the replicating the final wavelength lambda F. Compton tried to calculate it with the theory that photons are hitting the electron and the collision is elastic. So what Compton did, he utilized the idea of conservation of, you see, because it is collision is elastic, he utilized the idea of conservation of energy and conservation of momentum to get that calculation done. Okay, so he utilized that idea of energy conservation and energy momentum for the calculation. Okay, so this is our entire methodology will be coming, but I believe that okay, what should I just present you the scheme and utilizing that conservation of energy and conservation of momentum theorem. Now, to do that, first you have to accumulate all the data. Okay, you have to make a data table like that. But I believe I should do that in the next class, because that also involves a bit of calculation. Okay, so wait for the next video lecture for the detailed calculation and further explanation of Compton effect. Okay, so thank you. Okay, just to get a glimpse, this is the way everything will go up. So I'll do that. Okay, these values are waiting for you. So wait for it. Next day, next class. Okay, we'll discuss it. Okay, how everything actually comes up. We'll explore everything. Okay, many open questions you have to explain, but wait for the next class. Okay, because that calculation itself is a very rigorous calculation. I will show you step by step how it comes up. Okay, will that entire calculation, the explanation that wavelength is actually changing. Ultimately, whatever I am telling, it's only words, only theory. You have to show that, to validate that through calculation. I will do that. Okay, and also you have to explain those two open questions: why X-ray is used, why electron elements of low atomic mass is used. So we'll do all, explore all these things, but wait for the next video lecture. Thank you.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me.